Okay, here we go. All right, you're just starting the lesson. We're continuing on with section 3.3 on trigonometric substitution. Okay, so somebody, I think it was Caleb, raised the very important question when I first showed you the first example of this. How do you know when to use which substitution? So let's begin there. There's three situations that arise. There's integrals involving the square root of a squared minus x squared for some constant a. There's integrals involving the square root of x squared minus a squared, so where that subtraction is flipped around the other order. And there's integrals involving the square root of a squared plus x squared. I don't need to write that one in the other order because it's the same thing, right? Because addition is commutative. Addition is commutative, subtraction is not, right? If you flip the order of a subtraction, then you get a genuinely different thing. But if you flip the order of addition, you get the same thing. So there's really the three cases. We want to think about integrals involving each of these expressions. And in this case, you want to use x equals a times sine of theta. And the reason is because then you will get 1 minus sine squared, which equals cosine squared. In the case of x squared minus a squared, you want to use x equals a secant theta. And the reason for that is because later on you will get secant squared theta minus 1. And that expression is equal to tangent squared theta. Do I have that right? Hang on, I have a moment of doubt. I need to check. I need to check the super ultimate trigonometric identity compendium. Let me do that real quick. Right. So yeah. So if it's this one. It's this one. If you do secant squared minus 1, you get tangent squared. Aha, okay, good. I remembered it correctly. Secant squared minus 1 is tangent squared. That's right. And you get a secant squared minus 1 out of that when you plug in a secant theta for x. And then lastly, for this one, you want to use, for this format, you use a tangent theta, because then you will get 1 plus tangent squared, which equals secant squared. So you can memorize these things, or you can sort of figure it out on the fly, because basically all of these, each of these substitutions, each of these replacements down here using trig identities, they're all using a version of the Pythagorean identity. If you just have to look at the Pythagorean identity and figure out which one is the right one. Right, so whatever trig function you stick in here, you're going to have that minus 1 or maybe plus 1 or 1 minus that. You just kind of look at which identity is arranged in a way that'll allow you to make a substitution with the square of an individual trig function, right? Because in this case, in all of these cases, you're then going to have the square root of this, which gives you the square root of a square, like so. And in each case, that square root of a square then simplifies like so, like so, and like so. So do you get the idea? So that's how we know, that's how we can know which substitution to make. So far, we have done an example with sine, and we've done an example with tangent. So let's do an example with secant next. Let's integrate 1 over the square root of x squared minus 25. Or, 25 is, we've been doing everything with perfect squares. Why don't we do one that's not a perfect square? Let's just do minus 5. If it was a perfect square, then we can use integers, which is nice, but let's do one that's not a perfect square. Why don't we use arc? There's a question in the chat. Why don't we use arc cosine or, oh, sorry, not arc cosine, but a times cosine? You certainly could use cosine. In fact, right over here, you could use cosine instead if you used x equals a times cosine theta. You would still get, 1 minus cosine squared, which is going to be sine squared, which has the benefit, which still has the effect of canceling the square root, right? So like you could do that, but I mean, they both work so that they're almost equivalent. The only difference between them is in this case, you get dx equals a cosine theta d theta, whereas in this case, you get dx equals negative a sine theta d theta. So, I mean, if all else is equal, but one of them has a negative sign and the other one doesn't, you might as well use the one that doesn't have a negative sign in it. That's why we tend to use sine theta. That's literally like the only reason. It's just because then we don't have to deal with an extra negative sign. That make sense? And similarly, these have alternatives as well. Like instead of using secant and tangent, you could use cosecant and cotangent, which end up with very similar results, except again, you've got extra negative signs floating around when you use cosecant and cotangent. So why would you bother having extra negative signs when you could just use secant and tangent and not have extra negatives? If you want to fill in your notes, by the way, you could just remind yourself, okay, when you're doing the differential substitution, you're going to get the derivative of secant, which is secant times tangent, right? So you're going to get all that. And when you do it here with the tangent one, you're going to get secant squared. So just don't forget that you've got to do not only the variable substitution, but also the differential substitution in order to complete the full change of variables from x to theta. That addresses that question and plus a little more. All right, so there we go. So now we've got this example over here, 1 over the square root of x squared minus 5. So it involves this expression. So what we're going to want to use here is x equals a times secant theta. Now, what is a going to be? Aha. Isa's got it for us there in the chat. It is indeed going to be the square root of 5 times secant theta, right? Because if this is x squared minus a squared and a squared is 5, then a is the square root of 5. Good. So then that's our x. Now we're going to do dx, right? Is that square root of 5 times the derivative of secant, which is secant theta times tangent theta, and then all of that times d theta. So now we can make both of these substitutions into our integral. What's that going to look like? 1 over the square root of the square root of 5 secant theta, all of that squared, minus 5. And then times, in place of dx, I'm going to put the square root of 5 secant theta, tangent theta, d theta. So I'm making both of those substitutions, right? This whole thing goes in there. This thing goes in there. Okay, so you can see that there is a little bit of there's a little bit of sort of compressing we can do here. Let's move all this jazz like basically up there into the numerator. I think it's going to be a little easier to write it out that way. So square root of 5 secant theta tangent theta over there. And then over, now in the denominator, we have this big square root. We square the square root of 5 and we get 5. And then we're going to be able to factor a 5 out, right? So we'd have 5 times secant squared theta minus 1. Is that algebra all right? Everybody comfortable with that algebra? Somebody just left. It's pretty good. So then you can see there is going to be a cancellation of square roots of 5 here, which is kind of nice. So square roots of 5 are going to cancel out. That's kind of handy. But then we're still left with the following. Secant theta times tangent theta divided by the square root of, and now we can do our substitution with a trigonometric identity. We can say, well, secant squared minus 1 by this version of the Pythagorean identity in here, that's going to be equal to tangent squared. So here we go. And then, of course, that means that in the denominator, the square and the square root can cancel out. Now, I'm thinking about whether we need to worry about the absolute value again, because remember, this is this oft forgotten fact from algebra class, right? That like these square roots and squares don't directly cancel out, at least not when you have them in this order. Square root of square sort of cancels out. It gives you the absolute value, right? Because of the whole idea that like a square root is a principal square root, not just like, it doesn't give you a plus or minus, it gives you the absolute value. It gives you the positive one no matter what. And I'm just thinking about whether we need to worry about the absolute value on this problem. Let me check on that. You need to worry about that? Can I just... It should be, it should come up in the example. Okay. So we're going to actually just, look at the textbook. It's a good book. Well, first let's compare and contrast, because going up here, if you look at like the first one, we have this absolute value of cosine of theta. When you do the substitution, the first example of the textbook is a substitution with like a sine theta, like the very first example we did of this. I think it was last week. If you have the absolute value of cosine theta, you don't have to worry too much about that, because the theta values are between negative pi over 2 and pi over 2 for sine theta. So cosine theta is always positive on that interval. So that's when it doesn't matter. If you are doing the x equals tangent theta substitution, and you, again, you make the 1 plus tangent squared is secant squared. Now your absolute value of secant theta is also still equal to secant theta. Secant theta is just the reciprocal of cosine. So whether you're dealing with cosine or secant, they're both always positive, again, on this interval from negative pi over 2 to pi over 2. But when you are working with with x equals a times secant theta, it gets a little bit messier because the interval you use for secant theta is sort of like, here, I'll draw a picture of it. Let's get that out of the way here. With secant theta you use is like same with cosine theta. You use the top half of the circle when you're dealing with secant or arc cosine or arc cosine or secant or arc secant. Use that top half right there, right? So that we're talking 0 to pi. But then what we got later is tangent of theta, right? After we did our substitution, we're looking at this right here and reducing it to the absolute value of tangent. Unfortunately, on this interval, some of the tangents are positive because the tangent of the angle, right, is the slope of the line that goes out at that angle. So these tangents, the tangent of this angle here would be positive. But if you take an angle over here, that is a negative slope. So what we really want to do here is kind of break this into cases. This is where it gets annoying. Because we have to say, well, this is going to be negative tangent theta. Okay, we're gonna have to flip the sign if theta is between like pi over 2 and pi. This would be like quadrant 2. Versus over here, we don't need that negative sign. We don't need that negative sign, extra negative sign there at all if we're in quadrant 1. That makes sense? It's only this case. The other two cases we already studied don't require this like breaking, like this like plus or minus kind of thing. Here's a question. Here's a comment. If the bottom tangent is negative, will the top tangent be negative too? Not really, because actually, here's the thing. It's not this negative sign. This negative sign is not there. Well, it's not exactly there because this is negative, right? So like basically this, what I mean to say is this negative sign is not that negative. It instead is the negative sign you need to apply to make a double negative so that you get back to the absolute value of tangent of theta. So basically in this scenario, you're actually looking at a negative number up in the numerator. Tangent of theta will be a negative number, and this is a negative number, which gives you a positive number in the denominator. So the minus there doesn't actually mean that the denominator is negative. Instead, the minus is there to make the denominator positive again. Does that make sense? Yeah, that's kind of, this is where, yeah, you probably all remember studying this sort of thing in trigonometry where you have to do like breaking into cases. It's kind of annoying, but unfortunately, this is the way it works. Another question. Oh yeah, Braden makes a good point. You know, these should be, we should really just be doing this. As for pi, I think, nope, you're right. Yeah, you're right. Both of those should actually be strict inequalities. We actually don't want to allow equals. And I guess the reason for that is because in the case of when actually being equal to pi over 2, your tangent of theta is undefined. And in the case of being equal to either 0 or pi, your tangent of theta is equal to 0, and then you have division by 0, which is likewise undefined. So, so there's another technicality there. We want to make sure we're not actually including those undefined cases. If this stuff, so I'm looking at Diego's comment, if this stuff about the plus and the minus is really confusing, you know, if you don't get the plus or the minus, that doesn't mean you're going to be taking an L, as you say. Like, it doesn't mean you're going to fail the quiz. It just means that you might not get 100% on the quiz, you know? Like, you might not get an A, you might get a B. Does that make sense? Like, it's not a total fail. You know, it's a relatively small detail in the large scheme of what we're doing here. So don't worry too much about it. But let's see how this pans out, right? So what happens here is these tangents are going to cancel out in both cases, right? So in one case, we have the negative integral of secant theta, d theta. In the other case, we have the positive integral of secant theta, d theta. Okay. So this looks all fine, except now we got to figure out what's the integral of secant theta. Remind me, maybe you guys remember, have we talked about how to integrate secant theta yet? Not yet? Yes? No? I'm guessing not we don't remember. Maybe? Isa remembers it. Isa's got a good memory. I think we did, yeah. Oh, that's secant theta plus tangent theta. Yeah, it is. Secant theta plus theta is sort of the trick you use. Let's do it real quick down here. What you can do here is, in order to integrate this, we can multiply by secant theta plus tangent theta in the numerator and denominator. So this is just a modification to the integral, like that. And then you can say, aha, now let's let u equal secant theta plus tangent theta. Du is then secant theta tangent theta plus secant squared theta, d theta. Now, this, if you check out what's going to happen in the numerator, I won't write the whole, maybe I won't even bother writing this step because I think you can kind of see what's going to happen. When you distribute the multiplication by secant theta, you're going to get a secant squared, which is that. And you're also going to get a secant tangent, which is that. So the entire numerator happens to match what we have here. Wow. Who would have predicted that, right? So that ends up, so what we end up getting here is the integral of 1 over u du. And so we have the natural log of the absolute value of u. And that becomes, then after undoing our substitution, the natural log of the absolute value of secant theta plus tangent theta. And then I guess a plus c. Now, if you want to, you could just memorize this. This is something you could just memorize. Given that this is hard to remember, like this step and this u substitution is kind of hard to remember. I have trouble remembering it. I always have to like look it up or something. I might recommend just memorizing this, or, you know, maybe I should put this on the reference document. That might be worth doing. I know you guys would like it if I did that. I'll consider doing that. So what we have here, let's use that now to go ahead and finish this up. We have the natural log of the absolute value of secant theta plus tangent theta. And then we still need to figure out how to undo the substitution and like get back to putting this in terms of x's, right? It's all got to get back in terms of x. So in order for us to do that, let's make some reference triangles up here. Or actually, we might only need one. So for this, we're just going to stick to the case on the right. Let's stick to the case where theta is acute. Okay, so if theta is an acute angle between 0 and 90 degrees, or 0 and pi over 2, then we can draw it in one of these it doesn't matter, just one of these angles here. And then let's label it according to the original relationship. So we got to go all the way back to the beginning. The original trig substitution we made was x equals root 5 secant theta, right? And so what that means, taking that, you rearrange it slightly, secant theta is x divided by root 5. And that's what we want to use to label our triangle. So secant theta, which is secant theta is a little bit weird because it's secant theta is it's the reciprocal of cosine. So cosine's adjacent over hypotenuse. So we want to go the other way around. We want to go hypotenuse over adjacent. So this is going to be, if that's x over root 5, it's going to be x over root 5, like that. Did I do that right? Secant. Yeah, that looks right. Yeah. So then we can say, all right, so root 5 squared plus whatever goes here squared is going to be x squared, and you can solve for this. So this is going to be x squared minus 5. And so our unknown side there is going to be the square root of x squared minus 5. So let's go ahead and put that in. Oops, my 5's getting a little messy. 5. Okay. And now, remember this? The whole idea is like, hey, this is, the square root of x squared minus a squared. Like that same exact expression is showing up. That's kind of, just embedded in this situation. It's like, yeah, the whole reason we're doing this stuff with secant is because of that expression, the square root of x squared minus 5. And yep, it shows up again in your triangle when you are, setting up the reference triangle. No coincidence, right? It's all connected. So now that we have our little reference triangle, now we can get in here and say, well, what's secant theta and what's tangent theta? So, secant theta we already had secant theta, I guess. That was just this. So that's just x over square root of 5. And then tangent theta is opposite over adjacent. So now I just use my reference triangle. It's going to be the square root of x squared minus 5 over the square root of 5. Absolute value plus c. There we go. So I only finished it out for one of the two cases. I didn't finish it for this case over here, but it's very similar. So let me back up here. There's a couple of things in the chat. Did we get everything okay? Did we get the I think it's okay, right? It's fine. Never mind. Okay, yep, we're good. Caught up on the chat. Yep, there's nothing else there. No more questions that I can see. Yeah, so it's another example. You guys should try this. You guys should try another one on your own. We have about 20 minutes. Let's do it. Let's do it in the Jamboard. So, if you could please navigate yourself over to D2L, then one of the links I provided over here is to a Jamboard. I don't think we've used the Jamboard yet in this class, have we? Let's see. I don't think so. Nope, it's blank. So help. This is a sort of a communal whiteboard space. So you guys can click on that link and then you'll show up here. So this is you all. Hello. You're all anonymous. So, be nice. Don't be mean. This is an anonymous space. Being anonymous is kind of cool because then you can be totally wrong and no one will know it was you. So it's okay. It's a good space to make mistakes and be wrong. And we can help each other out. Lots of ways you can interact on here. If you have a stylus or you don't mind writing with your mouse, you can use the pen. You can change the color of the pen if you want. You can edit, undo. It's nice and simple. Or you can use your eraser. Haha, I broke your line. If you want to type, you can also type, x squared plus 1 equals whatever. You can type. You can also post little stickies. I don't understand this part here. Can someone explain it? You could do that just to make little comments. And then so you can kind of communicate with each other that way. And that's pretty much all I would use. I mean, there's circles and image. You can add an image, but you probably won't need to do that very often. But yeah, these are kind of nice ways to all sorts of different ways you can interact. What I recommend doing is also having something, having a paper. So you're working on paper. Maybe you can kind of go back and forth between your paper and the Jamboard. But the idea is that you will then be sort of collaborating to solve some problems. So I'm just going to give you all one problem, and then you can kind of distribute yourselves across several pages. Let's have 5 pages, and you guys can distribute yourselves across the 5 pages and just sort of form 5 groups. And within each group, you'll be working on it. But then if you want to go peek at what the other groups are doing, if you get stuck and you want to peek at the other teams, feel free to do that. I think it's fine to do that. And so I will give you a problem to work on. So let's make it, I'm going to pick one from the homework over here. Why don't you guys do, this one, 138. I can't remember if I assigned that one or not. If I did, that's fine. But let's do this one. Oops, no, that's not where I wanted to go. So I'll post that on the Jamboard and let you guys get to it. And then I will also be watching. Oh no, you guys, it's getting very messy. I'm sorry, I'm just gonna delete that one. And give you guys a new one here. Okay, there you go. So work together on this. I will be following along. I'm just going to turn my mic off for a while and watch, and then I might participate with little comments. I think you guys can see me, right? Do I show up as anonymous, or am I you see my face and my cat? You guys can see me? You can see my picture? Okay. It's actually my parents' cat. A lovely cat. He has since passed away. He was great, but he lives on in my profile picture. All right, I'll leave it up to you guys to work on this, and I'll be here if you need me. Hey, folks. So we're down about 2 minutes. Let's take a look at what you did. So I'm back recording again. Took a little pause from the recording, but so let's see how you're doing. There was a group here starting from the second page. It got pretty far. Most teams were getting close. So let's take a look at this one. After doing the substitution, you get like sine squared over cosine and then times cosine. So the cosines cancel out. You just get the integral of sine squared. And I saw that over here as well. See, in the third group here, we're getting sines, just sine squared. And then, yeah, we learned how to do that. We learned how to do the integral of sine squared. You use a power reducing formula and get 1 minus cosine of 2 theta all over 2. So that was going great here and here. Now that integral you can solve with a u substitution. So we do that. We get like a fourth u minus a fourth sine of u. But then, of course, we want to undo the substitution and put the 2 theta back in again. So I'm going to look at this page here. This team was doing great. We got theta over 2 minus sine of 2 theta over 4. So we went from u back to theta, but now we got to go from theta back to x. That's where the reference triangle comes in handy. And here's our reference triangle with x and 1 minus x squared. And then we can say, okay, well, sine of 2 theta, I like this here. We have to use yet another trig identity. I guess you don't have to, but I think it's most convenient to use this trig identity. This is what I showed you to do as well, right? Oops. I'm not syncing, apparently. But once you get sine theta and cosine theta, right, each individually from the double angle formula here, then we can get in there and replace sine theta and cosine theta with some expressions involving x. We get this. Now, the one thing we're missing here is, what about this theta? What happens like in this first term where we just got theta? We don't have like a trig function of theta, so we can't use the reference triangle. But what we could do is just use the original substitution and just get an inverse trig function. So like the original substitution was x equals sine theta. So you could say, since x is sine theta, theta is just arc sine x, and that'll just have to do. So that arc sine x is what you put in place of theta there. Okay, not as good as having an algebraic expression like you can on the second term, right? If you can use a reference triangle, you can get it to be in terms of algebra as opposed to trigonometry. But if you can't do that, well, that's okay. I guess we'll just use the trigonometry. Yeah, so that's how we wrap it up. Question here, does a half arc sine x minus a fourth sine 2 arc sine x work? So Issa's asking, can you just use arc sine everywhere and just put this arc sine in like here? I mean, you can. That would be a correct answer. But, and this is kind of where it gets a little bit subjective. Generally, it's generally agreed upon that an algebraic expression is preferable to a composition of trig and inverse trig functions. So that second term where you have sine of 2 times arc sine, like right there, you might as well simplify that with algebra. And that's what we're doing here. So by writing it as 2 sine theta cosine theta and then using our reference triangle to plug in expressions for sine theta and cosine theta, we get a nice algebraic function instead of that nasty trig composition. So, like I said, a little bit subjective. It's just generally agreed to be preferable to write it in the algebra way. Does that make sense? So, see you guys tomorrow. That's it.